We're doing vector calculus, chapter 2 of calculus, part 1, where we're going to do vector differentiation and the unit tangent vector. So we will go through the theory quickly and then we'll do some test type and exam type questions. So as you can see here, in part 1, we will do vector differentiation and the unit tangent vector. Then in part 2, we will do the arc length. Part 3, we will do curvature. Part 4, we will do torsion. And then in the last video, we will do the trajectories and orthogonal trajectories. So we will have 5 parts, so just make sure you watch them all from the beginning. So just to run through the theory quickly, so if we have a vector function RT, so we can have in 2 dimensions and 3 dimensions. So we have RT, we have in 2 dimensions xt, yt, and in 3 dimensions xt, yt, zt. So now it depends whether you're working in 2-dimensional or 3-dimensional space. So then to get the derivative of that vector, we derive component-wise. What do I mean by that? So we will derive our x component separately and we will derive our y component separately, and then in 3D our z component. Just remember at Wits that we also write it like this, or with a dot. That means dr dt. Just always indicate that you are doing the vector. Now, as you can recall from first year, the derivative with respect to t, where RT is our 2 or 3-dimensional curve, the derivative to this curve or the derivative to that vector will be the tangent vector to the curve defined by R at a specific point. So just remember that we change a curve into a vector, and hence the vector calculus. But more on that later. So just remember, when you do the derivative, make sure that it does exist and that the derivative is not 0, because since it defeats the point if the tangent vector is 0. So in the case where RT is the displacement vector at a time t, just recall that the derivative is the velocity vector and the second derivative the acceleration vector. Now, what we're going to do, very important. So if we are getting a vector in parametric form, so let's just stay in 2 dimensions. So that is my parametric form. So when I do the derivative, I will derive x and y separately. Now, if I get, so we're going to have to run through the 3 types quickly. If I get my z in terms of a complex number, so xt plus yti, remember we change it to a vector. Since we're doing vector calculus, our x component will be xt, so our x component is the real part, our y component the imaginary part. We do not take the I with. So to change a complex number into a vector, we use the real and the imaginary part. So that is our complex curve, and we change it to a vector. Then the third one that you need to focus on, if we get our curve in the form at e to the I bt, then what we will do, very important, but I will explain it later, we will have two methods to actually find the derivative dr dt, but more on that just now. So these will be the three different forms that we need to focus on when we do problems. Now, very important, just rules of differentiation. You all know, so if u and v are differentiable vector functions of t, and phi t is a scalar function of t. So in other words, if you get anything like that, for instance, it is a scalar function in terms of t, then as you can see here, you are going to do the product rule. More on that later. Here you will, if c is a real number or scalar, you'll just take it outside, and this you are familiar with, the derivative of a sum of derivative. Then when we have the derivative of a dot product, also the product rule. Just focus on the dot product between the vectors, and then the same for cross product. But we do use the product rule. Now, like I said here, if we have our curve in this form, and we need to get our derivative or our tangent vector, what we can do two methods. What we're going to do here, I'm going to show you method 1, and then I'm going to show you method 1 and 2, and then you can decide which one you prefer to do in tests and exam. Method 1, what you will do, you will first change, as you can see here, your e to the I bt to cos bt plus I sin bt. Very important. If you have watched all my videos, so if you watch the algebra videos on complex exponentials and complex logs, you will see that we did use it a lot. We also used it in D operators. So that's very important. But now, what did I say just now? If you have your curve as a complex function, you will write it as a vector. You will have your real part and your imaginary part in your vector. So there I have now my zt. But what will I do to get dzt? I will do the product rule. So what will I use? I will use this one, this rule. Since I have the product of a scalar function and a vector function of t, and I use the product rule. What do I have here? Product of a scalar function and a vector function. Product rule. So the derivative of at, my vector as it is, plus at as it is, derivative of my vector. What did I say earlier? We do component-wise derivative of cos bt minus b sin bt. Derivative of sin bt, b cos bt. So, what will I do here now? So this is all from first year. Remember, you want to get dz dt first, then you want to get the vector form of dz dt. So, what did we do in first year to get the vector form? For the x component, I am going to add all my x components, which is I will distribute that in. So, I will have derivative at cos bt. What is my x component here? It's at times minus b sine bt. There I have my x component. Now I'm going to do my y component. So let's do the y component. I will distribute in. I will get a prime t times sine bt. There I have my first part, and then I will distribute in here. I have my second part, ATB cos bt. So as you can all see here now, I have my vector y because I have my x component and my y component, and that will be my vector form of dz dt. Now this vector form of dz dt, we will call that our r prime t, or we will call it dr dt. So very important, the vector form of dz dt is your dr dt. So I want you really to remember that for later. Now remember I said there are two methods. Method 1, what did I do? I've changed that straight away into cos and sine. But what do I do in method 2? I do not do that. I go straight from here and I derive with the product rule. So let's run through that quickly. The derivative of a prime t, keep e to the power of ibt as is, plus then at as is. The derivative of e to the ibt is ib times e to the power of ibt. Now what I suggest you remember from now on, what I'm going to use a lot, is taking out a common factor of e to the power of ibt. What is left in my brackets? A prime t plus at ib. So that's when I take out my common factor. But remember, I want my vector form of dz dt. A vector form will never have an imaginary part. What is the only thing I can do here? I'm going to change my e to the ibt to cos bt plus r sin bt. There's my bracket. And what I'm going to do now, remember what I said, your vector form will never have the I in your answer. So what will I do here? I am going to start distributing. So to distribute to find my real part, I do first term times first term, hence this part. What do I do to get my second real part? I will times outside 2. Why? Because I times I is I squared, which is -1, as you can recall from all the videos on the complex numbers. Therefore, I have my real component. So just to recap, to get your real component, you can times your first 2 terms in both brackets, and then you add and you times the last 2 components in your brackets. Now to get the imaginary part, I will do the outside terms, and I will get sine bt. We can actually first do that. The outside 2 is bat cos bt, and then I can do the inside. So it is sine bt a prime t, and remember I don't take the I with, and there I have my vector form of dz dt, which I will call dr dt. Very important. So I'm repeating the sentence again here since you must really focus on that, and please memorize it, but never in maths just memorize, really understand it. dr/dt is the vector form of dz dt. So you can do other methods, but more on that later. Then I did paste the theory here, what you'll see, what you're going to use a lot, but I want you really to study it before you attempt any examples or test questions. Again, the squared identities, I'm sure you are all familiar with that. I'm not going to waste time with it. Your double angle formulae trick from first year. And then we have, very important, we have the hyperbolic identities. Please familiarize yourself with them. If you haven't studied it before, now is the time before you attempt any questions. Those three we're going to use a lot. You can actually just ignore these two for now. Now, let's start with the questions. First, we're going to do vector differentiation. Now, I'm not going to waste time on the easy ones. If you have a curve that is represented by a vector, you can see it's in 2D, and they say find the tangent vector. You will just derive component-wise. Derive this part to get that, derive second part. So I'm not going to waste time with these. You can do it. And when you study for a test or exam, just remember that you need to study your derivatives of the hyperbolic functions. So just to recap, the derivative of cos hyperbolic t is sine hyperbolic t. The derivative sine hyperbolic t, and the derivative of sine hyperbolic t is cos hyperbolic t. There are no sines involved. So that is very important. But as you've noticed by now, I use derivatives a lot, so you really need to know your derivatives. Then we have the next one. As you can see, you just need to know your derivatives. But now, what I just want to explain here, if you have a curve with that equation, what do you see is happening there? You have your derivative. In terms of a scalar function times a vector. So I'll rather write it like this. You have your scalar function times some vector. What will you do? And that's the reason why I did go through these earlier. These are very important, especially this one where you're going to do the product rule. A common error from students is that they're not aware of that and they do funny things. What students like to do, they will first distribute in. Please never do that in this section. So what will I do? The product rule, let's run through it. You will derive et, it stays e to the power of t, you keep your vector as is, plus then e to the power t as is, then the derivative of your vector component was minus sine t cos t, 0. Remember, whatever we do in this section, we work with vectors. So you want to get this in vector form. What will you do? Now, what I also want you to remember here, do not distribute if you have a common factor that you can take in. We only distribute if we do not have a common factor. We have a common factor here, so we take that out. Now we will add the components. X component cos t minus sine t. Y component sine t plus cos t, 1 plus 0. And there we have our tangent vector. In case RT was given as a displacement, your derivative of RT will be your velocity vector. Now, another one that I just want to stress here to make 100% sure you understand. So, if I have this curve in the complex plane, why complex? Because of the imaginary part. And by now, I'm sure you've noticed that we do work in the complex plane a lot. So, if you haven't watched the algebra videos on complex exponentials and complex polynomials and complex logs, please do so at some stage way before the exams. Now we're going to find the velocity vector. But what did I say earlier? It's everything in this chapter is about vectors. How do we change this to a vector? A vector, it's the real part and the imaginary part. I do not take the I with. And then from there, I'm going to derive component-wise. Please, a common mistake students make because they're in a rush and they're not focusing and they do not realize that that is the product rule. Now, the one that I want to definitely quickly do is, for this one, they're asking you have the curve in the complex plane again. Why curve in a complex plane? Because we have this in exponential or Euler's form. So because of the e to the I pi t there. Now they want us to find the velocity vector. So we want to find dr dt. Now, as mentioned earlier, what do you see you can do two methods? So what I'm going to do quickly, to save time, I'm not going to do it the first method way, but you can recall the first method way I changed my Euler form. Please do not forget that Euler is cos theta plus I sine theta. By now you've noticed that we use it often in algebra as well as calculus. So you can try method 1 by yourself. I myself prefer to use method 2, but it doesn't matter. It's whichever method you are comfortable with. So let me go through this one quickly. So what I said earlier, I will from here straight go to my product rule in my method 2. So I derive d squared is 2d. I keep e to the power of I pi t as is. Then I keep 2 squared as is. Now I derive this one, which is I pi over 2 times e pi over 2i. So just maybe rather put your I in the numerator so that you don't get confused there. Now, what did I say earlier? Please remember for this section of the work, actually in all maths, we always look for a common factor to make our life easier. So what I did here, I could actually take out the 2 also as a common factor, but I took out this as a common factor. What am I left with? I'm left with 2t plus pi I over t squared. What am I going to do now? Now I change my Euler form to cos pi over 2t plus I sine pi over 2t, and I have my second bracket. Also, a common mistake that students make, when they use Euler form, they actually leave the pi over 2 out. No, you have to take that whole angle. So please make sure you focus on that. Now, what's the next step? What I'm going to do? What did I say earlier? For my vector form. Because, please remember the sentence, dr dt is the vector form of dz dt. Now, as you all can see, here I have dz dt, but I have i's in here, so I need to find my real part. That will be my x component, and I need to find my imaginary part. Just recall from earlier, for the real part, I will times the first two components, hence this one, then I will multiply the last components. Why? Because I have I squared, which is negative 1, and then I get t squared pi over 2 sine pi over 2t. Now, recall what I said earlier. For your imaginary part, you will times outside 2 and inside 2, and you will not include the I. That's what I have done there. And there I have my dr/dt. Just one thing I also want you to remember for tests and exams, you have to indicate when you are doing a vector with a line underneath the R. Very important. Now, let's go. We did our tangent vector. So what we're going to do quickly, we are going to do our unit tangent vector. Now, just recall from first year, what is a unit vector? Unit means 1, so the unit vector has length 1. Now, if you can remember from first year, if you have a vector AT and it does not have length 1, how do you change it to a unit vector? You will say AT divided by its magnitude. So you can get your unit vector or your vector in that direction. So in most textbooks they use the double line for the length of the vector, but in this course we will just use the single line. So I just want you to recall, to see, yeah, I'm doing the unit, the keyword unit, tangent vector. Hence, I'm changing my tangent vector to unit vector. Therefore, I do r prime over r prime magnitude. And just to recall, when you do r prime magnitude, it is the derivative of the x component squared plus y component squared rooted, and then the same in 3D. Magnitude, very important for the next video when we do arc length, for the third video when we do curvature, and so for torsion. So this is extremely important for what is coming. So let's just look at this quickly, because before we focus on the important ones, here they will give you the curve in vector form, and they ask you to find the unit tangent vector. But before you find the derivative, now you do the magnitude of the derivative. Please just remember that we are going to use a lot of double angle identities. So familiarize yourself with these ones that I did pasted here. So these are all from school or first year. You should know it quite well at this stage. So that's the reason why I won't waste time with this, but it is my advice that you do change in maths the double angles always with your double angle identities to simplify your answers. So sine 2t to sine t cos t, and cos 2t to cos squared minus 1. So if you only have the cos 2t, you can either use 2 cos squared minus 1 or 1 minus 2 sine squared. squared t. And then what did I do? I simplified the numerator, and then what did I do? I divided each component by the denominator. So that's important. The next one, you will just for later, is extremely important to know your hyperbolic identities. The hyperbolic identity is cos hyperbolic squared t minus sine hyperbolic squared t is 1. And that's why I've changed sine hyperbolic squared plus 1 to cos hyperbolic squared. So make sure you go through this example yourself. Now, this one I will just quickly also say here, when this is a trick you need to please remember when you're studying. We did this now before when we did the derivative. Now, I don't want you to distribute in. No, leave that common factor outside when you do the magnitude, because that makes your life easier. Leave it outside. Why can we leave it outside? Because when we do the magnitude, we in any case do that squared. And the square root of e to the t squared will just be e to the t. Hence the reason why I leave it outside. Then I will go my first component squared, my second component squared, and then my third component squared. So that's why I said you leave your scalar function on the outside of the square root. Now I will times out. That's from school. I'm not going to waste time with it. You simplify, and then one thing you can always remember, cos squared plus sine squared with the same angles will always be 1, and there is your answer. But that's your magnitude for your unit tangent vector. You will go your derivative over the magnitude of your derivative. So now you can also see why I leave my scale outside, because most of the time it makes my life easier with the simplification. I can cancel, and there is my unit tangent vector. So I'm not going to do this one now. I think we must go to this one straight away, the last one. So you have your curve in the complex plane. They ask you for the unit tangent vector. I just want you to remember what I always say in my videos. You look what they're asking for. They're asking for the unit tangent vector, and straight away that should always be your first step. Unit tangent vector is to write down your formula, which is r prime t over r prime t magnitude, or as they write in your study guides, it is with a little dot at the top, magnitude. Familiarize yourself with all the different notations. Now, just recall earlier that we did do the derivative. So remember there were those two methods. I preferred the second one, but whatever is easier for you, you're going to use in the test. And then remember, dr/dt is the vector form of dz dt. So what I did here again, I looked for a common factor, but a common mistake students make. So please remember, if you have a vector, you take out a common factor from both of them, so you are left with that. So that's a common mistake from students that you must please look out for. So there I have my tangent vector, dr dt. Now we have done dr dt, we need to do dr dt magnitude. What do we do in magnitude? We are going to to take the t out, we can take the t out, so let me rather just redo this one here. So remember I said you can take the scalar out when you do the magnitude. Remember now I'm doing magnitude, and I did say you can take that outside. Now what am I going to do now? Remember it's your x component, and just make sure you copy everything perfectly from your derivative. They do not mark according to your mistake. They don't follow it through. So please make sure you do copy from your previous solution properly. So we have the x component of the derivative squared plus the y component of the derivative squared. Now what I'm going to do, so just see if you can follow here. I'm going to do for the first bracket, I'm doing the first component squared plus the second component squared. You'll see now why I'm doing it. Sine squared pi over 2t. Then I will do the inside just now. Then for the second bracket squared, I'm also going to do the first component squared, and I'm going to do the second component squared. Cos squared pi over 2t. But, so I just want you to remember what I'm doing. I'm doing first component squared, second component squared. Now I'm going to do a times b times 2. So I'm doing that for both brackets. Now I'm just going to write below it, but please try and write small in the test. Do not write in 2 lines. So now I'm going to times the 2 together and times by 2. So I get cos pi over 2t, and times by that one is t pi over 2 sine pi over 2t. What did I do there? I did this times by minus 2. Now I do the same here. I'm doing exactly the same there times by 2. So I get sine pi over 2t, t pi over 2 cos pi over 2t. Okay, so what do you see? Why did I do it like that? This is exactly the same as this. 1 plus 1 minus, so they will cancel. These two will cancel. That's why I did it like this. Let's see what we get here. And remember, this was still under the square root. Can you see those two? I'm gonna group them together. Why? Because it's sine squared and cos squared, and my angles are the same. Look out for that. And I take out 4 as a common factor. So those two together will be 4 times 1, 4. Now I will group these two together. Why? Same angle. So I'm doing this one and this one, same angle, but I have this common factor outside, so I have t squared. Sine, I have t squared, sine squared plus cos squared, yes, but I still have my pi squared over 4. Pi squared over 4. So I just want to make 100% sure you did what I do, you understand what I've done. So I've taken that component out. I do this bracket squared plus that bracket squared. But for this bracket squared, I did inside squared plus outside squared. So I did that first, and then later I times these two by 2, and I did the same with that bracket. So now what am I left with? I am left with my dr over dt magnitude is d. What am I going to do here? I'm going to get a LCD. So let's just write that here. I had 4 plus d squared over 4. Very important. So I get my LCD 4. So I have 16 plus t squared plus t squared pi squared. So for that part, very important. So just make sure you have familiarized yourself with all my steps that I've done. Now what I do, square root of 4 is 2. So what do I do there? I will say it is t 16 plus t squared pi squared. Square root of 4 is 2, and I have that on the outside. So that is very important, all these steps, since we're also going to do this later. This is going to be extremely important for later when we do curvature and torsion. So just remember that we now only got the magnitude of the derivative. So what do we end off with? We end off with magnitude of the derivative divided by magnitude of derivative. What is this? It's your unit vector, your unit tangent vector. So what do I do now? This is my answer for the denominator. My answer for the denominator is 2 over 2, 16 plus t squared pi squared. This was my answer that I've just done for the denominator. The answer for my numerator was, remember, this whole fraction here. So I'm not going to write it now. This whole vector will go over there, and you have your unit tangent vector. So quite a lot of maths that you're really going to have to focus on in the test, since they don't mark through with your mistake. So just to recap quickly for this video, we did the differentiation of a vector function, and then we did the unit tangent vector. So those are the two things you must really familiarize yourself with, and then just the different types of functions that I did derive. So in the next video, we will do the arc length for vector calculus. This is the end of vector calculus, the first video on vector differentiation and the unit tangent vector.